So greetings. So welcome to today's class. So if we recall, we were looking at performance specifications of dynamic systems, and we saw that like we typically specify performance by looking at first order and second order systems. So in the previous class, we started off with the second order systems. We saw that what was the general governing differential equation for second order systems. We got the transfer function. And then like we saw that depending on the value of the damping ratio zeta, the poles of this system can have multiple characteristics. So when the damping ratio zeta is between 0 and 1, we get complex conjugate poles, and we get what is called as an underdamped second order system. And we saw where the poles lie in that case at minus zeta omega n plus or minus j omega d. And please remember this definition of beta, okay, particularly tan beta and cos beta, okay. We'll be using them in today's class. And then like when we have zeta to be equal to 1, we have what is called as a critically damped system. Then we have two repeating poles on the negative real axis as minus omega n. Then when zeta is greater than 1, we have two distinct poles on the negative real axis at minus zeta omega n plus or minus omega n times square root of zeta squared minus 1. So this is the overdamped second order system. It's quite sluggish in nature. And then we looked at the concept of a dominant pole, and that's where we stopped. Okay. So typically what we do is that like when we work with second order systems and try to specify performance, we once again consider the unit step response. So let us start with that today. Okay, so let us consider the unit step response of underdamped second order systems. Okay, so we want to analyze or investigate the unit step response. And as we know, unit step response means U of S will be equal to 1 by S. So what we have is that like by now, all of us are familiar with this process, right? So Y of S will be P of S times U of S. And as we know, the transfer function is going to be omega n squared divided by S squared plus 2 zeta omega n S plus omega n squared. This is the transfer function. Of course, now we need to multiply by 1 by S, so I'll have a S here, right? So that's what will happen. Okay. So now, like I'm just going to do a derivation, which will also make it very clear as to how do we handle partial fraction expansion and taking inverse Laplace transform when we have second order factors which cannot be factorized into two first order factors in the denominator, okay, of the transfer function. So previously we had considered second order factors, but we could essentially factorize them as two first order factors with real roots, right? So, but now, as we know, for an underdamped second order system, we are going to have complex conjugate roots, right? So what is an alternative way of doing the same exercise? So the partial fraction expansion in this case can be written as A by S plus, when we have a second order term in the denominator, the numerator factor will be a first order factor, okay, in the form Bs plus C. And the denominator will be S squared plus 2 zeta omega n S plus omega n squared. Okay, so that's what will happen. Okay, so this is what will happen, and I leave this as an exercise to you to do. Some of these things I'm going to leave this as an exercise. So please find out the values of the residues. A will come to be 1, B will come to be minus 1, and C will come to be minus 2 zeta omega n. So I'm leaving this as an exercise for you to do. So please find A, B, and C. Okay, so this is how they will split up. Okay, so this step, I'm giving the answer. I'm leaving this as an exercise for you to do. All right. So if you face any issue, please let me know and we can discuss in the next class. Now, what we do is that like we just simplify this. We simplify as follows. We write it as 1 by s minus s plus zeta omega n divided by, let's see what I write and then I'll explain. It will become very obvious as to what I'm doing, right? So I'm just going to split this 2 zeta omega n as zeta omega n and zeta omega n, right? So I'm going to split this as two terms. So the first term will be s plus zeta omega n divided by s squared plus 2 zeta omega n s plus omega n squared. Then the second term will become minus zeta omega n divided by s squared plus 2 zeta omega n s plus omega n squared. Okay, so I'm just rewriting that same expression, okay, as two separate expressions. Okay, so this is what we do. Now we are going to do something interesting. Okay, so essentially we're going to do what is called completion of squares in uh, polynomial theory. You know, particularly when we deal with polynomials that are going to have complex conjugate roots, right? So let me tell you what this is, right? So I'm just considering the polynomial in the denominator, which is s squared plus 2 zeta omega n s plus omega n squared. Since this can be written as two factors involving complex conjugate roots, we are going to follow a slightly different process. So what we do is that like we first take this factor, okay, involving the factors of s squared and s, and we are going to rewrite in this way. So what we will do is that like we will write the s as the coefficient of s divided by 2. The coefficient of s divided by 2 is going to be zeta omega n. Okay, the coefficient of s is 2 zeta omega n. So I divide it by 2, I get zeta omega n. So s plus zeta omega n whole square minus whatever we wrote down, right, as zeta omega n, that's square. Okay, so we essentially write it like this. So if you expand this, you will see that you will get this. Okay, so these two are the same. Okay, so this is what is called sort of completion of squares, right? So what we do is that like we take the s squared term and the s term, we divide the coefficient of s by 2, we write s plus that term whole square, and then we subtract the square of the constant term from this first term, right? So if you expand, you will get s plus 2 zeta omega n s plus 1 zeta squared omega n squared, but then you also have a minus zeta squared omega n squared, right, which cancel. So you will see that we get the same answer, right? So I hope that is clear. Then we have plus omega n squared, which is remaining, all right? So that's one. Now, if we go further, what will happen is that like this can be written as s plus zeta omega n whole square minus zeta squared omega n square plus omega n squared. Okay, so that's what we have. Then what happens is that like we have s plus zeta omega n whole square plus omega n squared times 1 minus zeta squared, right? That's what we have, this term, right? This term I'm rewriting in this way, okay? So that's what we have. And what is this? This is nothing but omega d squared, right? Because omega d is defined as omega n times square root of 1 minus zeta squared. So omega d squared is going to be omega n squared times 1 minus zeta squared, right? So this we will get it as s plus zeta omega n whole square plus omega d square. Okay, I hope it is clear how we did this exercise, right? So this exercise is what is called writing this second order term with the complex conjugate roots as a sum of squares. So why is it called sum of squares? Because we have the result as sum of two square terms, right? One term being s plus zeta omega n, another term being square of omega d, right? So this is what is called as sum of square representation, or essentially expressing this thing by in a square, essentially a square sum, right? So that's what we are doing. Okay. Having expressed this as a sum of squares, so before we go further, let me do an example. So that like we get a feel of what is happening. So suppose, let's say we have s squared plus 2s plus 2, okay, which is going to have complex roots. if I want to rewrite in this form, what I do is that like I take the coefficient of s, which is 2, divide by 2, I get 1. So I write it as s plus 1 whole square. Okay, this is what is completion of squares. And then like I subtract the square of the constant term, which is minus 1 square. And then anyway, I'm going to be left with, right? So when I am doing completion of squares or sum of squares, I get the result as s plus 1 whole square plus 1, right? So because this is minus 1 plus 2 is anyway 1, which I can anyway write it as 1 square, right? So that's why I'm getting it as s plus 1 whole square plus 1 square. Okay, so I hope this, right? So this exercise is what is called completion of squares or expressing the sum of squares. Okay. Now going back to y of s, we will get this as 1 by s minus s plus zeta omega n divided by s plus zeta omega n whole square plus omega d square minus zeta omega n divided by s plus zeta omega n whole square plus omega d square. Okay, so I'm just rewriting that above expression, okay, in this form. All right, so that's all I have done. All right, so now we essentially go back and look at some properties of this Laplace transform. You remember one property where I wrote down that the Laplace of e power at f of t, right? That is, we consider taking the Laplace transform when we multiply a function with an exponential function, right? So this becomes f of s plus a, right? So we are going to apply it here. So we are going to consider two specific cases. Suppose if I have Laplace of e power minus at cos omega t, that will become, wherever s appeared, I substitute s plus a, right, in the expression for Laplace of cos omega. So I will get s plus a divided by s plus a whole square plus omega square. Okay, so that's what will happen to the expression for Laplace of e power minus at cos omega. Sorry. Now, similarly, if I write the Laplace of e power minus at sine omega t, I will get s plus a, sorry, not s plus a, omega divided by s plus a whole square plus omega square. Okay, so that's what I do. Okay, so now we can immediately map. So what we called as a in that expression is essentially zeta omega n, right? So we can look at that. And what we called as omega in this expression is omega d. Okay, so you can see the mapping, right? But if you go to the second equation, we have zeta omega n here, s plus a, and then like we have omega d, but the numerator is zeta omega n, but that can be easily addressed. Let me write down what we do. So we do this minus 1 by s plus, minus s plus zeta omega n divided by s plus zeta omega n whole square plus omega d square, okay, minus zeta omega n divided by omega d, right? I multiply and divide by omega d, so that like I make the expressions consistent with the formula that we just wrote down. So we get omega d divided by s plus zeta omega n whole square plus omega d square, right? So now we are almost there, right? So if I want to simplify this zeta omega n by omega d, I can do that also. So zeta omega n divided by omega d can be written as zeta omega n divided by omega d is omega n times 1 minus, square root of 1 minus zeta squared. The omega n and omega n can cancel off. So I will get zeta divided by square root of 1 minus zeta, right? So that's what we have. Okay. So now we are almost done, right? So just one more step and then like we are done. So consequently, what will happen is that if I now take the inverse Laplace transform, what are we going to get? We are going to get the inverse Laplace transform of 1 by s is 1. And for the second term, we are going to get e power minus zeta omega nt cos omega dt. I'm sure we know how we got this, right? So we just apply this formula, okay, for the property of the Laplace of cos omega t multiplied by e power minus at, right? The a is zeta omega n, omega becomes omega d, right? So that's how we got this. So we applied this property. And if we look at the second one, we also can immediately rewrite it, right? So that's going to be minus zeta divided by square root of 1 minus zeta square e power minus zeta omega nt, okay, sine omega d. Okay, so sine omega d. Okay, so that's so essentially this is the expression for the unit step response of an underdamped second order system. Okay, so we get 1 minus e power minus zeta omega nt cos omega dt minus zeta divided by square root of 1 minus zeta square e power minus zeta omega t sine omega d. Okay, so any questions about this, till now, before we go and interpret this expression? I hope it is clear how we got this, right? So once again, we can see that exponential functions are coming in, and one can say, hey, what happened to the exponents, right? Initially, we saw that the exponents were all like, we mentioned that, the exponents should be the poles of the system transfer function, right? But the exponents here are only the, what to say, the real part of the poles, right? So minus zeta omega t. That can be easily understood because I can always write e power minus, what to say, let's say I take plus j omega, right? So e power minus zeta omega n plus j omega d t. Okay, if this is one exponential term, I can rewrite this as e power minus zeta omega n times e power j omega d. Okay, and e power j omega dt, I can express it as cos omega dt plus j sine omega dt, right? So now you get the point, right? So the poles are still the exponents. It's just that when we have complex conjugate poles, the complex part comes out as cosines and sines, right? Due to this simplification. Okay, so that's all we are doing, right? So I hope that is clear, right? Now, also, as time t tends to infinity, we can immediately observe that y of t tends to 1. Okay, so I'm sure all of us can observe that. Why? Because although we have cos omega dt and sine omega dt, we can immediately see that there is an e power minus zeta omega and t multiplying the cos and the sine terms, right? And the exponent of that is negative, and so as time increases and goes to infinity, that e power minus zeta omega and t will go to 0, right? So consequently, that will become the product of that e power minus zeta omega t cos omega dt and e power minus zeta omega t sin omega dt will go to 0. Consequently, we will be left only with 1. All right. So that's how the steady state output will become 1. So I hope even that point is clear, right? So now let us plot this unit step response. Okay. So I want to plot y of t versus t, and then let's see how it is. Okay? So let's say this is a steady state value of 1. And we want to plot this, right? So if I want to plot this, the way it will look like is this, something like this, sorry. Nice curve. So it will overshoot, it will oscillate around 1, and then it will keep oscillating, and then it will settle down. Okay, so you can see that it is going to have oscillations with the frequency of omega d, right? That's why it's called as the damped natural frequency. So I hope now it is clear why this omega d is what is called as the damped natural frequency, right? Because the oscillations of the unit step response happens at a frequency of omega d, okay? And what to say, the because of this exponential with the negative exponent, the oscillations keep on getting damped, okay, as we go along, right? But the frequency of oscillation is omega d, okay? So I hope now the meaning behind why omega d is called as the damped natural frequency is clear. So now the question that arises, is the following: what parameters quantify or characterize this unit step response? Okay, so what do I mean by this unit step response? The unit step response of underdamped second order systems. Okay, so that is a question we are going to answer by proposing some parameters. All right, so let's do that. Okay, so what is the first parameter that we will consider? The first parameter that we will consider is what is called rise time. Of course, here I'm going to do some exercises and I'm going to leave some exercises to you as homework. Okay, so let's do that. Okay, but before we go to the derivation of rise time, any questions on what we have learned till now? All right, so let's continue. So what is this rise time? Okay, so let me write down the definition and then we will derive expressions also.
Sir, if we plot the y of t, we'll get the same kind of curve in any of the plotting tools with 1 minus e
I
power.
didn't get you. No?
Sir, if we plot
So
equation like 1 minus e power minus zeta omega n t,
correct.
so we'll get a same this curve like what
Yes.
it is damp. Oh,
Yeah.
okay.
So if I understood the question, if I can paraphrase it, suppose let's say you substitute some value of zeta and omega n, right?
Yeah.
And then you plot this curve. This is how it will qualitatively look. Okay. Yeah.
Okay.
Okay. Yeah.
So why are we always, giving a step input as a input? Like, we can use a ramp input or any other type, right? But
Absolutely. So it is just that these parameters have been specified with means of a step input, although they are pretty challenging to achieve in real life. Okay, so in real life you can never generate an ideal step input, can you? Right? But it's just that when we use a step input, the theoretical analysis comes out very nicely. So that's how conventionally it is used. Okay? And that is, see, another, in fact, easier input to use, theoretically, which is pretty intuitive, is the impulse input. Because if you take the spectrum of the ideal impulse signal, you will see that all the frequencies are excited, okay, to the same extent. So essentially, it is pretty, useful from a theoretical point of view. But once again, the challenge comes to the practical implementation of it, right? Yes, if you ask me, yes, it is difficult to generate a step input, but we try to go as close as to a step input as possible. That's why when I talked about typical inputs, I also include ramp because see, in real life, what we may be able to generate, right? Let's say even we do so-called step seer test. Okay, let's say when we consider cornering performance and so on, right? So let's say this is my steady state value. I may be able to do only this, correct? Something like this. Is it not? Right? So
right.
then the question is, what I am asking is that like how much is this time interval compared to my overall time interval or the time response of my scale of time response of my system. Suppose if this is of the order of, let's say, like 100 milliseconds, right? And the system responds in, let's say, 5 seconds. Okay, I will say 100 milliseconds is very small when compared to 5 seconds, right? At least I can neglect it, right? So that way I will argue and then like still use step response and the theoretical results coming from the step response to analyze. On the other hand, if the system responds in 0.5 seconds, so then I need to be a bit careful, right? 0.5 seconds is 500 milliseconds. So then I can no longer reason out that 100 milliseconds is very small when compared to 500 milliseconds, right? It's 20% of it. Okay.
Right.
Then I need to consider this as a sort of like a ramp input which is saturated. Like, so I may want to analyze it more carefully. All right. So,
whatever, sir, you classified in the previous lecture, like 4 or 5 points, like if it is on the j omega axis or on the left-hand plane, we categorize that, it will be stable, it will be unstable, it will be bounded and unbounded, right? So
yes.
there we classified for step and, sinusoidal inputs only. So what about the other inputs, sir, which will be coming under what category?
So if you look at that classification, that was for all bounded inputs. Okay, please. Okay, so step and sign happen to be bounded inputs. Okay, if you take the pure ramp input, it's always unbounded, right? Why? The ramp input as such, right? So
Right,
if I
increases.
plot the ramp input, the unit ramp input, right? So if I plot u of t equal to t, it is unbounded in magnitude. It keeps on increasing with unit speed, right? So similarly, if I take the impulse input, that is also unbounded, right? Because instantaneously at time t equals 0, its magnitude goes to infinity, etc. Okay.
Right.
So
Yeah.
that is why some people will talk about steps and signs, right? But the discussion I made was for all bounded inputs. See, for example, we may have an input like this. See, in real life, this may be a more practical input, right? I ramp like this, I hold it constant, and then I bring it down like a trapezoid, right?
Yeah.
So this is a bounded input. So the results that we discussed for bounded input, bounded stability have hold true even for these trapezoidal signals. Okay? Yeah. Okay.
What
So
is the significance of zeros, sir? Like we are discussing only about the poles, but the zeros on the S plane, like when we solved that homework problem, we got 1 zeros and it is coming on the LHP. So, but like how is it exactly significant, sir?
okay. So okay, good. So let's go to the homework problem. Okay, so let's just all right. Okay, so I think this was the second problem, right? So I have solved this, right? So I hope all of you have uploaded your solutions, like I'm discussing it with that assumption, okay? So, so in fact, if we refer to this problem, right? So now we have a 0 at -3, right? Is it not? So what happens is it like when you compare it with the unit step response when there was no 0, the poles were the same, but the 0 alone like was not. This is what we have, right? So you recall when the transfer function was just 1 divided by s squared plus 3s plus 2, this was our unit step response, correct? So now with this 0 in place, we have a different unit step response. So immediately by comparing these two what to say output functions, we can make two observations, right? So immediately with the introduction of a 0, see, 0 doesn't play a role in determining the stability of the system. Okay, the stability of the system is dependent only on the location of the poles. Okay, point number one. But where do zeros come in? Okay, poles still come as the exponents in the exponential term. Okay, that is also influenced by the poles, right? You can see e power minus t and e power minus 2t terms, right? One can observe that since both poles are the same for both the problems, the system response is still stable. Now, we can see two effects, right? The first effect is that the residues of the exponential terms are different, right? So we have -2 multiplying e power minus t term. Here we have +(-1) multiplying e power minus t term. Okay. By coincidence, the residue of e power minus 2t term happens to be 1/2, but that's a coincidence. Okay, not true in general. Okay. So point number one, there is a change in the residues of the coefficients multiplying the exponential terms. Okay, due to the introduction of a 0. Then what also happens is that like the steady state value also changes, right? So in the first case, when there was no 0, the steady state value is 1/2, right? But in the second case, where there is a 0 at -3, the steady state value becomes 3/2, right? So that also happens. So in essence, the stability is affected by the poles, right? But the exact shape of the transient response and the steady state value are affected by both the poles and zeros. Okay, so I hope the physical, what to say, effect of zeros is not.
Yeah, right, sir. I was curious, like, if we have a, S-3 term and or, some other term where, some imaginary components come on the zeros, still it will not be having any impact, sir. Only whatever the residues you are saying, that will be the change.
So what will happen when SC is equal to +3? What do you think will happen based on our discussion that we had? So you remember the non-minimum phase zero, correct? So if
Yes.
SC is equal to +3, once again the residues will change. Okay, so whatever I discussed till now about zeros hold true. But when you come to non-minimum phase zeros, you will have this sort of response. Okay, in addition to whatever I discussed. All right. So you can also have complex conjugate zeros. Absolutely no problem.
Okay.
So if I have to summarize the overall response, to this question, the poles affect the stability of the system. Okay, the stability of the system is captured by the location of poles. We want all poles to be the left of complex for stability. Okay, no doubt about it. Now, the zeros affect the transient response and the steady state value by influencing the coefficients that come about in the output function. Okay, that's what it is. So, in essence, the shape of the output function and the steady state value are affected by both the poles and zeros, whereas the poles decide whether the output is going to be bounded or unbounded for all bounded. Okay, that is the difference.
Okay, sir. Thank you.
Is that clear? No, sir.
Yeah.
Yeah. So that's a very good question, because we need to have an intuitive idea, right, as to what a pole and a zero are doing, right? So that's very important. All right. Any other questions before we go for quantification of these parameters? Okay. So essentially, rise time. What is rise time? Let me write down the definition. Okay. So we are trying to quantify based on the unit step response of an underdamped second order system. The rise time T subscript R is the time taken by the system to reach 100% of the steady state value for the first time. Okay, so that is what is rise time. Okay, so what is rise time? So essentially, it is this. So 100% of final value is 1 in this case. So the question is that, like, what is the time at which this happens? That is the rise time. I hope it is clear, right? So now, if I want to calculate the expression for rise time, what do? I essentially figure out at what time the output becomes 1, right? So that is what I need to. So this implies that the expression for the output is this, e power minus zeta omega n. Instead of t, I substitute tr. I take e power minus zeta omega n t common from the last two terms. So as a result, I will have cos omega d tr plus zeta by square root of 1 minus zeta square sine omega d tr, right? So, okay, and that should be equal to 1. Okay, so this I get it from the expression for the output function, right? So we can immediately see that 1 and 1 get cancelled off, right? And then we are left with 1 being equal to 0, e power minus zeta omega and tr multiplied by that term in the square bracket. But then this term, e power minus zeta omega and tr, is not equal to 0 for a finite value of tr. Is it not? Because the rise time is not infinity, right? So we know that the exponential with a negative exponent will go to 0 when we go for infinite time, right? But then here rise time is finite, right? So this is not 0. So then the only conclusion is that the second term in the square bracket is 0, right? How did I come to this conclusion? Say, suppose if we have the product of two terms, A and B, to be equal to 0, right? The consequence should be that A should be 0, B should be 0, or both should be 0. But in this case, the first term is not 0, right? Because PR is finite. So that's why the second term is 0. So once we have this, we just simplify. So this will give us cos omega d PR plus divided by square root of 1 minus zeta square sine omega d PR. That's going to be equal to 0. So then we can essentially simplify this, and I can get tan omega d PR to be equal to minus square root of 1 minus zeta square by zeta. Okay, so this is something I can try. So immediately by taking the inverse tan and then dividing by omega d, I can rewrite this as 1 by omega d tan inverse of square root of 1 minus zeta squared by zeta. That's going to be the expression for my rise time. Okay, so this I'm going to write as pi minus beta divided by omega d. Okay, can you tell me how I can do this? I made a remark at the beginning of today's class, right? Remember the expression for tan beta and cos beta, right? So can you tell me how I went from the first expression to the second? Of course, beta should be substituted in radians. Okay, let's go up and then like see what we wrote down for tan beta. So if you recall, tan beta was square root of 1 minus zeta squared by zeta, right? So, but then we had tan inverse of minus square root of 1 minus zeta squared by zeta, right? So let's go down and write it down, right? So recall that the beta was tan inverse of square root of 1 minus zeta squared by zeta, right? So this is something which we know, right, from that expression. And tan inverse of minus x is essentially pi minus tan inverse of x. Okay, so that's what we have. So tan inverse of minus square root of 1 minus zeta squared by zeta, I can write it as pi minus sub beta. Okay, so that's how we got that expression. The main catch is that like we should substitute beta in radian. Okay, so we should not substitute beta in degrees. Okay, so I hope this derivation is clear. All right. So immediately we can observe one thing, right? So as the value of zeta decreases, the rise time also decreases. So that means that if I make the system more underdamped, okay, I keep on decreasing the value of zeta, the rise time decreases. If the rise time decreases, the system responds only faster, right? So that is something which is advanced, right? Is it not? So I faster response from the system, right? So, but then is to pay, like nothing comes free. Okay. Recall in the previous class, I mentioned that like typically as a rule of we essentially try to underdamp systems, like where the damping ratio in 0.4 and 0.8, right? So we will sort of see why we do this, right? So of course, if I take the damping to be less than 0.4, if I keep on decreasing from 0.4, I'll get lower rise time, right? But that's going to, right? What is the difference? Let's look at that now. Okay. Yeah. Any questions on the rise time? So if there are no questions, let's go to the peak time. So I am going to leave the derivation of the remaining expressions to you as a whole, as homework, as exercise problems. You don't need to submit them, okay? But then please do them as exercise problem, okay? So, but then you can ask me questions class if you have any doubts. Okay, I will explain the physics. I will tell you how to get the expressions, but you please get the expression. So what is this peak time? Peak time is this. Peak time is the time taken output to reach the first peak of its overshoot. Okay, this is called as the overshoot. Okay, what is called first overshoot. Sorry. Okay. So this is what is called as the first overshoot. So why is it overshoot? You can observe that the output is overshooting or going above it's what to say intended or like value, right? So this is called as a first overshoot. Okay, so the peak time is the time at which it gets overshoot, and the corresponding value, let's call it as y at tp. Okay, y tp is the value of the output at the first overshoot. Okay, so please this condition. So now the question is, how do I get this from this expression? I think everything is obtained from this expression. So I'm sure from basic mathematics, if you want to find the maxima or minima of a function, what do we do?
So derivative will be 0 here.
We need to solve for derivative equals 0, right? And then we also need to take derivative to figure out where the become negative to find, right? Is it not? Correct? Yeah. So we can immediately observe that at peak, the function will be value, right? So I need to find the first maximum, right? What I need. Is it clear? So, and the function is y of t. What should I do? To solve dy dt equals 0. So please solve dy dt 0. If you do this, what will happen is that you will get t be equal to n pi by omega d. Okay, where n is equal to 1, 2, etc. Okay. This is not the maxima. It includes both maxima and the local minima, right? Now, what you need to do is that take the second derivative, okay, and where it is negative, okay, because maxima, right? So, and in this particular case, we want to essentially get, of course, you will see that you will get the for an odd multiple n, and since we want for n equals 1, answer for the peak time will be pi by omega. Okay, so this will become very simple at the end. Okay, I leave this as an exercise for you to do. Please do it. Okay, so as derivative, you can see that this is one application. Differential becomes very useful, right? So we are essentially using ideas of maximization and minimization to do this. So this is the expression for peak time. Then comes what is called maximum peak overshoot. So what is this maximum overshoot? MP, write down the symbol indicated as M subs. So what is this maximum peak overshoot? By definition, MP is as y at TP minus y t tends to infinity divided by y at infinity multiplied by 100. Okay, so that is maximum peak overshoot. All right. So that is the expression for maximum peak. This also I leave it as an exercise. You substitute for TP in the expression for y. Okay, find y at TP, and then you simplify this expression. You will get the maximum peak overshoot of e power. You write it very, very carefully. So you will get it as e power minus zeta pi divided by square root of 1 minus zeta square. So minus zeta pi divided by square root of 1 minus zeta square is the x, okay, of the exponential term. So this It means typically people will express a percentage measure. Okay, so this is the expression for the maximum peak overshoot. Right. So once again, what you do is that like you substitute the expression for P in Y, the formula for Y that we derived in today's class, and then you simplify this, you will get the expression, right? So now we can figure things out, right? So as we told that as zeta decreases, PR decreases, right? Which is good. But then from the above expression, MP increases. Okay, so that is a problem. Okay. On the other hand, as we increase zeta, MP decreases, but TR increases. Okay, so this is a tough choice, right? So in the first case, what it means is that like if I make the system more underdamped by decreasing zeta, I make the system respond faster, but then I have increased magnitude of oscillation. Okay, the oscillations become higher in magnitude, right? So that is the issue. All right. So on the other hand, if I increase zeta, lower magnitude of oscillation, which is good. Okay, we don't want too much oscillation, right? But then what is the trade-off? System becomes sluggish, right? Why? Because the rise time increases, right? So that is the trade-off, right? So this is the reason why we tend to design as a rule of thumb. There is nothing set in stone. Second order systems, like with damping ratio between 0.4 and 0.8, right? I hope that is clear. All right. Okay. So I hope this sort of like clarifies why we want second order systems with damping ratios between 0.4 and 0.8, right? So, okay. Yeah. Because there is an inherent trade-off between the speed of response and the oscillations, magnitude of oscillations, right? Yeah. So choosing zeta between 0.4 and 0.8 sorts of gives a trade-off between the two. Now, as the last once again parameter, we are looking at settling time. Let us say we once again draw a band around the input. Now we draw a lower band and upper band, right? Because the thing oscillates around the final value. Let's say, like we essentially can consider a plus or minus 2%. Some people will also consider a plus or minus 5% band. Okay, by default, we consider a plus or minus 2% band. And the point is when the response, right, is within this band, we essentially take the time as a settling time, TS. Okay, so the settling time TS is once again taken as a time elapsed after which the output settles down within a band around the final value. Okay, so that is the last parameter that we will be looking at. Sorry. So settling time TS, it is a time taken for the output to settle within that band. And once again, this also I leave it as an exercise for you to do for underdamped second order systems under study. It is 4 divided by zeta omega n. If we consider the 2 plus or minus 2% band, okay, it is 3 by zeta omega n. If we consider the plus or minus 5%. Okay, so this is the difference. All right. So I hope it is clear how we got the settling time. Of course, I'm leaving this expression derivation as an exercise for you. But these are the formulae. So as I keep on mentioning, by default we will consider the plus or minus 2% band. Okay, unless otherwise explicitly stated. All right. Okay. So these are some parameters associated with underdamped second order systems that we use. Okay, so let me stop the discussion for today's class here. So in the next class, we will look at some more concepts associated with performance metrics. And then we will also look at what is called as frequency response. Okay, so let me stop today's class here. Are there any questions?
So when we say it's sluggish response, it means it's a highly damped system.
Yes, sluggish response means that the damping ratio is higher, right? So let's say the damping ratio is 0.9, right? So the peak overshoot will be low, right? But then the price will be that it will be sluggish.
Okay, sir.
So see, for example, just to draw a qualitative plot, let us say, sorry, I will just plot this and then we will stop. Okay, so let us say we want to plot y of t versus t, right? So for three damping ratios, right? Let's say first is a low damp ratio, okay, low damping ratio. So let me say this is the steady state value of 1. So for, let's say, low damping, this may be this is very fast, right? But there is a huge peak. So for high damping ratio, what will happen is that the peaks may be smaller, but then you see that the response time is slower, right? So this is what happens as zeta increases.
So definition of sluggishness will depend upon system to system, right? So we cannot say that well, this system is sluggish here. The similar system will be sluggish for the same value.
It depends on what we want, right? That's why these are performance metrics. This is only relative, right? So it's relatively slow. Okay. But then if you are fine with this response, we go with this. That's it. So once again, as I told, this is only a rule of thumb. Okay. It's not set in stone. Okay. Please note that. All right. So this is a convention.
Sure, sir. Thanks.
Yeah. Hey, any other questions? All right. So if not, let me stop recording. Okay. Thank you for attending today's class.